I had a question about the Otto cycle and just want to clarify a few things. So let's start with a sketch of the Otto cycle on a PV diagram. So isentropic compression from state 1 to 2, constant volume heat addition, so it's constant volume process to state 3, isentropic expansion to state 4, and then constant volume heat rejection back to state 1. So those are the four processes for the Otto cycle. All right, let's start with just finding our temperatures quickly. So T2 equals T1 times V1 over V2 to the K minus 1. And that comes from the equations for an isentropic process, ideal gas, constant specific heats. And then we can write V1 over V2 as our definition of R, or the compression ratio. So since I may have a lot of these, I sometimes write RV12, which means the volume ratio for process 1, 2. So then finally there, T2 equals T1 R to the K minus 1. So this isn't a new equation, this is just a familiar equation, one of three. Those three equations come from PV to the K equals a constant for an isentropic process. There's another one, P2 over P1, so these equations, PV to the K equals a constant, which using the ideal gas law, which is PV equals RT, this first equation can be written in a couple different ways. This first equation can then become P1 over, let's do P2 over P1. Let's erase that. P2 over P1 equals V1 over V2 to the K. So that's one of the forms. And then if I use the ideal gas law, I can replace these with R and P, and I get that P2 over P1 equals T2 over T1, and with some algebra I get to the power K over K minus 1. So all I did was just replace the V's in my first equation with RT over P and bring all the like terms to the same side. And then the final one is T2 over T1 equals V1 over V2 to the K minus 1. So these three equations has to be an ideal gas, constant specific heats, and an isentropic process. It's a mess. And this first process is isentropic. It is, for all of the processes, an ideal gas, and for all the processes I'm assuming constant specific heats. So I'm going to do this problem with this assumption. So I have T2 equals T1 R to the K minus 1. Again, my compression ratio is defined as V1 over V2, and I also define a pressure ratio as P3 over P2. So given that, if I use the ideal gas law for the second process, then I can write that P3 V3 equals RT3. I'm going to divide this though by P2 V2 equals RT2. And so the R cancels since both equations have R in it. And then I note that V3 over V2 is equal to 1, and so the pressure ratio is the same as the temperature ratio, in which case T3 just simply equals T2 RP. Then process 3 to 4, I have a similar equation as the first one, so I can write that let's do this as T3 over T4 equals V4 over V3 to the K minus 1. And in this case, V4 over V3 is also equal to R, since this is on the PV diagram V3, it's also V1 rather. V1 and V4, and this is V2 and V3. So V4 over V3 is the same as V1 over V2, which I've defined as R. So finally I get T4 equals T3 times 1 over R to the K minus 1. So now I have all my temperatures. Then I'm going to use the ideal gas law, the first law, Q minus W. Of course, it equals delta E, but I can write delta E as delta U if I'm neglecting change in potential and kinetic energy. And then delta U I can write as M delta U for constant specific heats. I can write M CV T final minus T initial, depending on what states. Of course, I'm assuming by writing that delta U equals Q minus W that the change in kinetic and change in potential is 0. Just so I have that in my notes. Okay. For the first process, it's isentropic, so let's write down a little table of our processes. So and I've got 1 to 2. Let me just try and give myself a little more room. One to 2, it's isentropic, so Q equals 0. Which means that using the first law, that I get W equals M CV, and it would be final minus initial, but W is negative, so it's going to be initial minus final, so it's going to be 1 minus 2. Which will give me a negative number, which it should be because it's work in, which is negative. 2, 3, it's a constant volume process, so the work is 0, and Q just equals from the first law mCV delta T. And I see I just wrote CP on the other one, so I'll fix that. T3 minus T2. Let me clean that up. mCV T1 minus T2. Process 3, 4. In this case, Q is 0 again. And I have mCV, want T final minus T initial, but it's negative, so T3 minus T4, which will be positive. And finally, 4, 1. In this case, constant volume, so the integral of PdV. If you're wondering how I know it's constant, dw equals the integral of p dv, and from 1 to 4 to 1, dv is 0. Okay, so q then is mcv, t final minus t initial, so that would be t1 minus t4, which will be a negative number, and it should be because it's q out. So now I have all my q, all my w, I have all the temperatures. I just plug in my values for mass, constant volume, specific heat, and I will get efficiency if I do that as 1 minus q out over q in would be one approach, or I could write that as the net work, all the work over q in. So I guess I better figure out which ones are q in. So this process 2 to 3, that's q in, and the only other q must be q out. Of course, we can tell by the sign, although it's not difficult to figure out. It's process 2-3 is constant volume heat addition. It's making the pressure go up and the temperature go up. But we can just follow the sign convention and get the right answers. So now I want to plug this in for efficiency. So I'm going to derive the equation for efficiency, and I'm going to put in, I'm going to use this first expression. So 1 minus q out is mcv, t1 minus t4, that's my q out, over my q in is mcv, t3 minus t2. Now there's a problem here, and the problem is that this equation knew that q out would be negative, and so the negative sign that's placed here already takes that into account. So even though that is my equation, if I'm going to write q out that will give me a negative number, I need to do the sum of all the q net divided by q in, and let the signs be what they may. And if I had done that, I would get 1 plus q out over q in. So by following the actual writing this q to where it will actually be a negative number requires that I don't put the negative sign in my efficiency equation. If that seems confusing to you, then just write that the network equals q net over q in, which is really what it is, and I just sum up all the q's, and if they're either positive or negative, I just put those in. Then I would get q in plus q out over q in, and that would give me 1 plus q out over q in. And then in that case, I would have to pay attention to the sign for process 4.1 and make sure that that comes out negative. So I'm going to continue on with this, and I get the m's cancel, the CV's cancel, and now I just have to put in all the equations for the temperatures. So I'm going to have 1 plus, and in the numerator T1, which is just T1, minus T4. Now T4 can be written as I have it, but T3 can be T2 RP times 1 over R to the k minus 1. But T2 can be written as T1 R to the k minus 1 times RP 1 over R to the k minus 1. And so we find out that those two terms would cancel, and we get that T4 just equals T1 RP. So let's put that in as T1 RP divided by, and then I have T3, which I saw here a minute ago is T1 r to the k minus 1 rp. So I'll write that. T1 r k minus 1 rp minus T2, which is T1 r to the k minus 1. And then I can divide the numerator in the denominator by T1, so this becomes a 1, this is gone, this is gone, and this is gone. I can factor out from the denominator r to the k minus 1 minus 1 minus rp over r to the k minus 1 times rp minus 1. And if I multiply by negative 1, so I'm multiplying, let me change that. Well, let me write that as a times negative 1. Then I can get rid of the positive sign and put a negative sign. And then what I get for the numerator is rp minus 1 when I multiply by negative 1. So the rp minus 1 cancels, and I have finally that the efficiency equals 1 minus 1 over r to the k minus 1, which is a nice simple result. And it turns out then that it's not, the efficiency is not dependent on my pressure ratio, but only the compression ratio. And I don't even need to know what T1 is or P1 is. So higher compression ratio gives me a higher efficiency for an engine. And unfortunately, I went a little bit off the page, so let me rewrite that somewhere you can see it. So the final result is efficiency equals 1 minus 1 over r to the k minus 1. And let me just rewrite. I guess you can see that. Okay, I was just zoomed in a little bit. So hopefully that, if I can get it to show up, maybe not. Well, I'll rewrite it. Let me erase and include that one final step that this came from. So as I started replacing terms, I had 1 minus negative 1 times 1 minus rp over r to the k minus 1 rp minus 1. And then negative 1 times 1 minus rp, which is rp minus 1. So those two terms canceled, and I got this final expression. All right, the question that came up is the pressure ratio of 3:2 equal to the pressure ratio 4/1? And I think we can see that from here. We have that T4 over T3 equals 1 over r to the k minus 1, and T2 over T1 equals r to the k minus 1. So let's give ourselves a little room here. And so I've got T2 over T1 equals r to the k minus 1. And I could rewrite this as r to the k minus 1 equals T3 over T4, just by multiplying both sides by r to the k minus 1, dividing both sides by T4. So those two things don't really need the r to the k minus 1 in the middle, they equal one another. And I could rearrange that as divide both sides by, if I get rid of what's in the middle, so T3 equals T3 over T4, I could divide both sides by T3 and multiply both sides by T1, and I get that T2 over T3 equals T1 over T4, or if I want to write that as T3 over T2 equals T4 over T1. And if you remember, when I used the ideal gas law, which I just erased what's underneath there, but we have P3, V3, T3, and P2, V2 over the other side divided by T2. And we said that this volume ratio is equal to 1. So the pressure ratio is the same thing as this is RP, is the same thing as the temperature ratio. So that means that T3 over T2 equals RP, and so T1 over T4 also equals RP. And if we give ourselves a little more room again, then P4, V4 equals RT4. I'll leave the R off for now because I'm going to write divided by P3, V3 over RT3. So I canceled out the R's. I can also cancel out the V's. And actually, let's do that not with 3 and 4. Let's do it with 1 and 4. So P4, V4, T4. It wasn't true for states 3 and 4, but it is for 4 and 1. P1, V1 over T1. So before I had V4 over V3, but those weren't the same volumes. That was R. But V4 over V1, if you look back at the PV diagram, well, you'll see those are the same specific volumes. That's what I was trying to do. And so I have that T4 over T1 is equal to P4 over P1. So that finally what we have from this is P4 over P1 equals P3 over P2, which is RP, and also that T3 over T2 is RP and T4 over T1 is RP. So yes, there's one pressure ratio for both processes where the pressure changes. That's not generally true. We proved it to be true. In other cases, the auto or the diesel and the dual and most others, there will be more than one pressure ratio.